Hello everyone, let us see the solutions for Polytechnic Lecturer 2024 ECE question paper conducted by Andhra Pradesh Public Service Commission. First question. For a type 2 system, the static error constant is 0.5. Compute the error for input t square by 2. So given input is t square by 2. So say it is r of t. So Laplace transform of r of t, so that is r of s. R of s, so its value is 1 by s cube, because we know that Laplace transform of t power n is equal to n factorial by s power n plus 1, n factorial by s power n plus 1. So according to this, Laplace transform of t square by 2 is 1 by s cube. Static acceleration error constant, that is Ka, is equal to limit s tends to 0 s square g of s into h of s. And they have given the value of acceleration error constant value is 0.5. So from this steady state error, given static acceleration error constant, so from this steady state error ESS is 1 by Ka, so that is 1 by 0.5. Its value is 2. Steady state error is 2. Let us see some more points related to this steady state error for different types of systems. For type 0 system with step input, for type 0 system with step input, steady state error is a by 1 plus kp. For type 0 system with ramp input, steady state error is infinity. Similarly for the parabolic input, for type 1 system with step input, steady state error is 0, with ramp input is a by 1 plus kv. For type 2 system, steady state error exists only for the parabolic input, that is a by ka. So this Ka, Kv and Kp are positional error constant, velocity error constant, and acceleration error constant. So positional error constant is limit s tends to 0 s into g of s. Velocity error constant is limit s tends to 0 s into g of s h of s. Ka is acceleration error constant, so its value is limit s tends to 0 s square g of s into h of s. Okay. If so, from this table, if input is greater than if input is greater than system type or type of system, then steady state error is infinity. If input greater than type, so for type 0 system, ramp input is higher. For type 0 system, parabolic input is higher. In this case, steady state error is 0. Or if system type, conversely, we can tell if system type less than input, then steady state error ESS is 0. If system type is less than input, suppose type 1 system for step input, so its steady state error is 0. System type are simply if type less than input, then steady state error is 0. So these are the some important points related to the question. Here where step input is a by s, ramp input is a by s square, parabolic input is a by s cube. Next question. Compute the closed loop gain of unity feedback system if open loop gain is 2 by s. They have given open loop gain is 2 by s. So open loop gain g of s h of s is 2 by s. From this closed loop gain of a unity feedback system, our forward function gain is forward transfer function gain g of s is 2 by s, and the unity feedback system, that is h of s is 1. Feedback network transfer function is 1. From this closed loop transfer function is g of s by 1 plus g of s h of s. So here we assume negative feedback system. So type of system is type of feedback is not mentioned. Consider negative feedback to solve this problem. Now g of s is 2 by s, 1 plus g of s h of s is 2 by s into 1. So that is 2 by s plus 2. So correct option is 1. Next question. Identify the closed loop transfer function of the following system. Given forward transfer function g of s. Given forward transfer function g of s is 25 by s into s plus 5. Given feedback network transfer function, that is h of s is 1. Unity feedback. Now closed loop transfer function is, so here it is plus and here it is minus. So it is negative feedback system. The transfer function of negative feedback system is, closed loop transfer function of negative feedback system is g of s by 1 plus g of s h of s. So replace g of s and h of s in this closed loop transfer function. The value 25 by s square plus 5s plus 25. So replace g of s with 25 by s into s plus 5. 1 plus g of s is 25 by s into s plus 5 into 1. So on calculation we will get closed loop transfer function is 25 by s square plus 5s plus 25. So correct option is 1. Next question. What must be done to have the same output if g of s is moved before the adder? So g of s is moved before the adder in the following system. So that is g of s is moved before the adder means shifting summing point. This is a summing point. This is a summing point, shifting the summing point ahead of the block. So, as per the diagram, C of S is R of S plus or minus X of S into G of S. If block is moved ahead of the summing point, so this is a equivalent diagram. So similarly for this diagram, expression for C of S, and for equivalent diagram, expression for C of S is G of S into R of S plus or minus G of S into X of S. If R of S is taken as common, then R of S plus or minus X of S. So both R of S and X of S branches will contain the G of S block. So R of S input and X of S input contains G of S block. Correct option is 1. Next question. Find the transfer function for the following block diagram. So here multiple negative feedback loops are given. So initially we'll start solving this question from the inner loop. So G2 of S, G3 of S, these blocks are in series. These two blocks are in series. So equivalent value is G2 into G3, G2 of S into G3 of S. So when two blocks are connected in series, then equivalent value is product of their individual gains. Equivalent gain is product of their individual gains. Inner block is this one. So this is a negative feedback system. So step 1, and for step 2, the resultant is evaluate the inner block, which is circled with the yellow line. Its corresponding transfer function is G2 G3 1 by 1 plus negative feedback 1 plus G2 G3, and corresponding feedback transfer function is H1. Next, evaluate this block. So now step 3 is to evaluate the blocks circled in red line. So this red line is positive feedback system, yellow line is negative feedback system, plus is mentioned here. Now the expression is resultant transfer function is G2 G3 by 1 plus G2 G3 H1. This is numerator 1 minus G2 G3 1 plus G2 G3 H1 into H of S value is H2 of S. This is the resultant transfer function for positive feedback system. This yellow line is negative feedback system and red line is positive feedback system. From this calculation, the resultant value is G2 G3 by 1 plus G2 G3 H1 minus G2 G3 H2. Next, evaluate the block circled with green color. Now again this step 3 is step 4 is it is a negative feedback system. Transfer function is same thing. The transfer function value obtained in step 2, that is G2 G3 by 1 plus G2 G3 H1 minus H2 H1 of S minus H2 of S by 1 plus G2 G3 1 plus G2 G3 H1 minus H2 into transfer function is H3. So from this we will get the equivalent value as G1 G2 G3. So that is no G1 is here, G2 G3 divided by 1 plus G2 G3 H1 minus G2 G3 H2 plus G2 G3 H3. Oh, again in the problem there is one more series connection, that is G1 of S. So G1 of S is also there, so we need to keep this one. So G1 of S. So this is a multiplied with G1. Now resultant transfer function is this one. So resultant transfer function is G1 G2 G3 by G1 G2 G3 by 1 plus G2 G3 H1 of S minus H2 of S plus H3 of S This is the resultant transfer function for the corresponding block diagram given. G1 of s, G2 of s, G3 of s by 1 plus G2 of s, G3 of s into H1 of s minus H2 of s plus H3 of s. So correct option is 1. Next question. For the following signal flow graph, match the following is given. Now V of s is, so from this signal flow graph, V of s is R1 of s, G1 of s minus R2 of s, G2 of s plus R3 of s and G3 of s. So V1 of s is fourth one. So this is V of s. Next, C2 of s. C2 of s is G5 of G5 V of s. So G5 into R1 G1. Next is C3 of s. So from this G5 of s into V of s. For C2 of s, this is a resultant. Next, minus C3 of s minus C3 of s. So that is minus of minus G6 into V of s. So that is G6 of s into V of s. So G6 of s into V of s. So this is minus C3 of s. C is 1. Next, D, C1 of s. So from this signal flow graph, C1 of s is G4 into V of s. So that is G4 of s into V of s. So D is 3. G4 into V of s. So correct option is 1. Next question. Compute the number of forward path gains in the figure shown below. So let us see the definition for forward path. Forward path is a path that can be traced through the graph from input node to output node without touching the node twice. The traversal of the path, or we can also say the traversal of the path from input node to output node without looping back. One more definition is forward path is defined as a set of branches that are traversed in the direction from input node to output node without touching any node more than once. Let us assume R of s is the input node and X of s is the output node. Here there are two forward paths. So this is one forward path, and next forward path is, so this is a forward path 1, forward path 2. Number of forward paths are 2. This is input node, output node. Next question. Find the damping ratio for the given system. So here, given forward network transfer function is G of s is equal to 25 by s into s plus 5, and feedback transfer function is 1. Its value is, feedback transfer function is unity. And the system is negative feedback system. Closed loop transfer function is G of s by 1 plus G of s h of s. The closed loop transfer function is 25 by s square plus 5s plus 25. Now the characteristic equation of the system is denominator part is 0. S square plus 5s plus 25 is equal to 0. Compare it with standard second order characteristic equation, that is s square plus 2 zeta omega ns plus omega n square is equal to 0. This is standard second order system characteristic equation. Now omega n square value is 25, so that is omega n is 5 radian per second, and 2 zeta omega n is 5. From this, zeta damping ratio is 1 by 2, that is 0.5. The damping ratio for the given system is 0.5. Next question. What is the steady state error for the following system if T of s is 6 by s square plus 8s plus 12 when excited by the step input signal? As per this block diagram, E of s by R of s is 1 minus T of s. So 1 minus T of s is, as per in the question, T of s is given as s square plus 8s plus 12, and also given R of s is step input, its value is 1 by s. Laplace transform of 1 is 1 by s. Now E of s is R of s 1 by s minus 6 by s square plus 8s plus 12. Steady state error value is, from this expression, steady state error is limit s tends to 0 s into E of s. Limit s tends to 0 s into E of s. E of s is 1 by s 1 minus 6 by s square plus 8s plus 12. S square plus 8s plus 12. Steady state error ESS. Now its value is 1 minus 6 by 12, that is 0.5. 0.5. Next question. Compute the phase response of a system. G of s is equal to 1 by s plus 2 s plus 4. G of s is open loop transfer function, or sorry, forward transfer function. G of s is 1 by s plus 2 s plus 4, that is s square plus 6s plus 4. 4 2 is 8. Sinusoidal form of above transfer function is replace s with j omega, then we will get the sinusoidal form of above transfer function. G of s replace s with j omega. So from this, g of j omega will become 1 by j omega square 6 j omega plus 8, that is 1 by 8 minus omega square. This is a real part, and imaginary part is j into 6 omega. Now angle of this transfer function g of s is minus tan inverse of tan inverse of 6 omega by imaginary part by real part. So this minus corresponds to the term in the denominator. Correct option is 1. Next question. Consider the following statement in the context of Nyquist criterion for a system stability. Identify the correct option. The poles of 1 plus g of h, 1 plus g of s, h of s are same as poles of g of s. So this statement is wrong, because the poles of 1 plus g of s, h of s are same as poles of g of s as well as h of s. It depends on both forward transfer function as well as loop transfer function. Next statement. The zeros of closed loop transfer function are same as zeros of 1 plus g of s, h of s. This statement is also wrong, because the zeros of closed loop transfer function are not necessarily same as poles of are not necessarily same as poles and zeros of 1 plus g of s, h of s. So we know that pole of a closed loop transfer function are the values of s that makes the denominator of transfer function 0. So let us assume this is a transfer function is g of s by 1 plus g of s, h of s. The poles of transfer function is defined as the poles of closed loop system are the values of s that makes the denominator of transfer function is 0, that is 1 plus g of s h of s 0. Similarly, the zeros of closed loop transfer function are the values of s that make the numerator of transfer function. So numerator of transfer function is here g of s is 0, or simply the roots of numerator transfer function are zeros, roots of denominator transfer function are poles. So from this, the zeros of closed loop system are not necessarily same as poles and zeros of 1 plus g of s h of s. 1 plus g of s h of s. So both statements are incorrect. Next question. Compute the number of zeros and poles in an open loop transfer function that has following Bode plot. Given for a given Bode plot, the initial slope here is minus 20 dB. So either pole or 0 corresponds to the initial slope. Now the slope is minus 20 dB. So there exists a pole at origin. Therefore, there exists pole at origin at omega 1. These omega 1, omega 2, omega 3 are corner frequencies. At omega 1, corner frequency omega 1, the slope of Bode plot changes from minus 20 dB to minus 40 dB as per the question. So there exists a therefore there exists a pole at cutoff frequency or corner frequency omega 1. Similarly, at omega 2, the slope of Bode plot changes from minus 40 dB to minus 60 dB. There exists one more pole at omega 2. Again, at corner frequency omega 3, the slope changes from minus 60 dB to minus 40 dB. Hence, there exists a 0. Increase in slope means 0. Numerator 0 at corner frequency omega 3. Therefore, the system has 1, 0, 3 poles. Pole at origin, pole at corner frequency omega 1, pole at corner frequency omega 2, and 0 at corner frequency omega 3. Correct option is 1. And a circuit consists of passive elements R1, C, and R2. Output is measured across R2. And input arm consists of series combination of R1 and R2. So here the input arm consists of series combination of R1 and R2, and output is taken across R2. So what kind of circuit it is? It is a lead compensator. The given circuit as per the question is lead compensator. This is a pole diagram representation of lead compensator, sigma axis and j omega axis in given in S plane. So in lead compensator, 0 is dominant over pole. 0 is dominant over pole. So 0 is close to origin. So this lead compensator is used for improving the transient state characteristics, that is improving the speed of system, improves the speed of system and improves the transient response. Next question. Identify the compensation technique provided in the given network. Here the output is taken across the series arm consisting of resistor and capacitor, and input arm is only simply resistor. So this circuit is lag compensator, and pole zero representation of lag compensator is given beside. So in this, for lag compensator, pole is dominant over 0. Pole is dominant over 0. The advantages of this lag compensator is to improve the steady state response. Steady state response of a system. Next, see some more points regarding one more compensator is lead lag compensator. So for this lead lag compensator, this is a represent diagram for lead lag compensator, and this is pole 0 representation of lead lag compensator, and this lead phase lag in low frequency region. So here from this pole zero diagram, phase lag in low frequency region and phase lead in high frequency region, and it is used for improving both transient and steady state response of the system. This lag lead compensator is used for improving both transient response and steady state response. So let us see the differences between lead compensator and lag compensator. Lead compensator and lag compensator. So in lead compensator, 0 is added. In lag compensator, pole is added. This 0 is added means differential term. Here it is integral term. This lead compensator is same as high pass filter. Lag compensator is same as low pass filter. Low pass filter. Next, here transient bandwidth increases. In lead compensator, bandwidth increases. Here the bandwidth of the system decreases. Lead compensator, system becomes more stable. System stability is increased. Increases marginal stability. Increases marginal stability. So here decreases marginal stability. So here marginal stability is increased means system becomes more stable. System becomes more stable. Decreases marginal stability means system becomes less stable. These are some more points related to lead lag compensator. Next question. Compute the steady state error for input 4 into u of t for the system shown below. Given forward path transfer function g of s is 120 into s plus 2 by s plus 3 into s plus 4. Given feedback network transfer function h of s is unity. From this steady state error is limit s tends to 0 s into r of s by 1 plus g of s h of s. So for input r of t 4 into u of t. Laplace transform of r of t is r of s is 4 by s. Substitute g of s, h of s and r of s in the steady state error expression. This is a steady state error expression for the given system. Limit s tends to 0, s into r of s is 4 by s, 1 plus g of s is 120 into s plus 2 by s plus 3, s plus 4, and h of s value is unity. Substitute limit s tends s value is 0, then we will get the steady state error ESS is 4 by 21. Next question. For the following system, for the following system, consider the statements and identify the correct option. Given forward path transfer function g of s is 200 by s into s cube plus 6s square plus 11s plus 6, and feedback path transfer function, that is h of s, is unity. Then from this on the feedback here given is negative feedback system. This is negative feedback system with the help of g of s and h of s. Then closed loop transfer function is g of s by 1 plus g of s into h of s. On solving, we will get closed loop transfer function as 200 by s plus 4 plus 6x cube plus 11s square plus 6s plus 200. So from this, make denominator part equal to 0, then we will get the transfer function by applying RH criteria to the transfer function. Routh-Hurwitz criteria: s power 4, s is cube, s square, s power 1 and s power 0. The values are 1, 11, 200, 6 and 6. So from this, equivalent value is 6 into 11, that is 66 minus 6, 66 minus 6 by 1, and its value is 200. Now 60 minus 200, 60 minus 200 into 6 by 60, and For s power 0 it is 200. For s power 0 it is 200. Now this 60 minus 200, 1200 by 60, it is negative value. So there is one sign change here, one sign change from this s square to s1, and there is one sign change from positive to negative and from negative to positive. So this is positive term and this is positive term. There are two sign changes, implies there are two poles in the right hand side of the s plane. Two sign changes implies system is unstable because two poles in right hand side of s plane, therefore system is unstable. Both p and q are correct and q is the reason for p. Next question. 6 dB per active is same as 20 dB per decade. So we know that 1 dB per decade is 0.3010 dB per octave. So from this 20 dB per decade is 6 dB per octave. Now octave to decade, its value is 1 octave is equal to 0.3010 into decade. This integral or derivative factors, derivative terms govern the initial slope of the Bode plot. The plot of open loop transfer function magnitude in dB and open loop transfer function phase in degrees versus frequency in logarithmic scale is Bode plot. So this is a definition for Bode plot. Bode plot is the plot of open loop transfer function magnitude versus open loop transfer function phase in degrees versus frequency in logarithmic scale. Next, for 6 dB per octave means equivalent to 20 dB per decade. Magnitude of S plus A. Magnitude of S plus A related to Bode plots. Replace S with j omega. Sinusoidal transfer function is A plus j omega. Its magnitude is A square plus 20 log of A. 20 log of A square plus omega square, and its value is A, provided that 20 log of square root of A square plus omega square, that is 20 log square root of A square. Square root of A square value is A if omega far less than A. So for second it is 1. Next is angle of S. S is j omega, so 90 degrees. Here it is plus 90 degrees. Magnitude of 1 by S. Magnitude of 1 by S. So 1 by j omega. So it is pole at origin, differential term at origin. It corresponds to the slope of minus 20 dB per decade. So correct option is 1. Next question. For the given root locus, compute the compute the open loop function in a closed loop system with unity feedback. So location of open loop pole from this root locus system. So poles are located at s is equal to minus 1 and s is equal to minus 2, and location of zeros is at s is equal to minus 3, s is equal to minus 4. From this open loop transfer function is k into s plus 3, s plus 4 by s plus 1, s plus 2, and the value of h of s is 1 as per the question. Now open loop transfer function value is k into s square plus 7s plus 12 by s square plus 3s plus 2. So open loop transfer function value is option is 1, and the value of k for marginal stability is obtained by determined or obtained by applying RH criterion to the characteristic equation. So from this open loop transfer function, calculate closed loop transfer function. So for this closed loop transfer function, obtain characteristic equation, and for this characteristic equation, apply RH criteria. Then the value of k is determined. Marginal stability value is determined. But our problem is restricted to calculate only the open loop transfer function. Next, match the following in the context of compensation technique. Here it is. There are four compensation techniques. Proportional controller, Kp is a propagation gain constant. Integral controller, Ki by S. Derivative controller, Kd into S, where Kd is a derivative gain constant, Ki is the integral gain constant, and combination of these two, proportional integral controller, proportional derivative controller, Kp plus Ki of S, Ki by S, and for proportional derivative controller, that is Kp plus Kd into S. For integration, for proportional controller, C, its value is 2 minus R2 by R1, proportional gain constant. For integration controller, its value is minus 1 by RC into 1 by S, Ki by S. So its value is Ki by S. And proportional derivative controller is given. Proportional derivative controller, its value is Kc into S plus 1 by Rc. For B, it is 4. For B, it is 4. And proportional integral controller, it is 1 by S, Kp plus Ki by S. Correct option is this one. Next question. System state equation and system output for a phase variable representation of transfer function g of s as follows. So state equation is given as x dot of t is derivative of d by dt of x of t is equal to a into x of t plus b into u of t, and output equation is y of t is equal to c into x of t plus d into u of t, where a is a system matrix, b is a input matrix, c is a output matrix, and d is a transition matrix. For the corresponding transfer functions, so for this system matrix is 0 1 minus 9 minus 7, and b matrix is, so b is, a is a system matrix, b is a input matrix is 0 1, and output matrix c is 1 2. Similarly, for this option b, system matrix is 0 1 minus 9 minus 7, and b matrix is 0 1, output matrix c is minus 1 2. Here output matrix c is 1 2, b is 0 1, and system matrix a is 0 1 9 7. So for this transfer function 0 1 minus 9 minus 7, and b matrix is 0 1, and c matrix is 2 1. A is system matrix, b is input matrix, and c is the output matrix. The correct option is 1. 0 1 minus 9 minus 7, 0 1, and 1 2. The correct option is 1. Next question. The poles of transfer function are the values of transform domain variable that cause transfer function to become infinite. When poles is denominator of transfer function is 0, poles are obtained when denominator of transfer function is 0. That is, when denominator of the transfer function is 0, then its value becomes infinite. Statement 1 is correct. Next, statement 2. Poles are any roots of denominator of a transfer function that are common to the roots of numerator. The poles of transfer function are the values of transform. So these poles are any roots of denominator of transfer function because these are common to the roots of numerator. Correct. For this, the reason is, for statement P, the reason is because these are the values of S that makes the denominator of transfer function equal to 0. Poles are values of S that make the denominator of transfer function 0. Values of S that makes denominator of transfer function to 0. If denominator is transfer function, numerator by denominator. In the transfer function, if denominator is 0, then transfer function value approaches to infinity. Its magnitude will become infinity. Next, correct option is 1. P and Q are correct, and P is not a sufficient and Q is required. Poles of transfer function are the values of Laplace transform variable s that cause the transfer function to become infinite, or poles is nothing but any root of denominator transfer function that are common to the roots of numerator. Both statements are correct, and correct option is 1. Next question. Consider the following statement in the context of a system. So for damping ratio, zeta is 0. The poles are, nature of poles are imaginary. Nature of poles are imaginary, and the system is, nature of the system is undamped. Undamped system for 0 less than zeta less than 1. If zeta lies in between 0 and 1, the nature of poles are complex conjugate. Complex conjugate with a negative real part. With negative real part. Complex conjugate poles with a negative real part. Here the nature of system is underdamped system. Underdamped system. If zeta is 1, the poles are purely real, equal and negative. So here system is critically damped. If zeta greater than 1, poles are purely real, negative and unequal. The system is overdamped. All poles of underdamped system are purely imaginary. Correct. Undamped system becomes underdamped if negative real part is added to the imaginary poles. Undamped system poles are purely imaginary, and undamped system will become underdamped if negative real part is added. Both statements are correct. Correct option is 1. Next question. Autocorrelation function is always an even function. True. So autocorrelation function r of tau is equal to r of minus tau. Or we can also write xs r xx of tau is equal to r xx of minus tau. So autocorrelation means correlation of signal with itself. So the definition of autocorrelation is correlation of signal by itself. That is called autocorrelation. So next, autocorrelation function is minima at zero lag. This statement is wrong. Autocorrelation function is maxima at zero lag. So zero lag means no time shift. Zero time shift. At zero time shift, autocorrelation value function is maximum. Q is correct, P is correct, and Q is incorrect. Next, relation between power spectral density and autocorrelation sequence. The power spectral density function is used to the autocorrelation of Fourier transform of autocorrelation function is power spectral density. Now autocorrelation function of a signal is defined as Rx of tau is expectation of x of t plus x of t plus tau. From this power spectral density of autocorrelation function is Sx of s is integral minus infinity to infinity Rx of tau, that is autocorrelation function e power minus j omega t into d tau. This power spectral density is real valued and even function, and this power spectral density is used to calculate the average or expected power in the random process. Both statement P and Q are correct. Next question. Consider the following statements related to white noise. White noise is stationary process whose power spectral density is 0 across frequencies. Let us see the definition of stationary process. A random process is said to be stationary if its statistical properties does not vary with time. White noise is a stochastic process with zero mean and constant variance. Now here, white noise is a stationary process whose power spectral density is 0 across all frequencies. It is wrong. Power spectral density is constant value across all frequencies. For white noise, autocorrelation function is impulse. This statement is correct. White noise, power spectral density is uniform. So power spectral density of white noise is uniform, and then autocorrelation function of white noise is delta function, that is impulse function. So P is incorrect, Q is correct. So this is autocorrelation function of white noise. Power spectral density and autocorrelation function representation for white noise. Next question. Compute the following by means of random filtering the signals through an LTI system. So impulse signal is given. The graphical representation of continuous time impulse signal is shown in the figure. So for this, the width of the pulse is 0. So that means pulse exists only at the origin, and height of the pulse is infinity, amplitude is infinity, and the area under the curve is unity. Let us see some properties of this impulse signal. Delta of t is equal to delta of minus t. That is, the continuous time impulse signal is even signal. Its nature is even signal. And the sampling property is integral minus infinity to infinity. Let us say some function g of t into delta of t is g of 0. This is sampling property, and shifting property is integral minus infinity to infinity. Let us say some function g of t or x of t, whatever it may be. X of t delta of t minus t naught into d of t is x of t naught. Then scaling property is lambda of a t is 1 by mod a, lambda of t where a is any positive integer, and product properties x of t into delta of t is x of 0 into delta of t, that is simply x of 0. And area under the curve for this impulse signal is unity. Now in the question they have given minus infinity to infinity g of t delta of t dt. It is related to sampling theorem, and its value is g of 0. Sampling property of impulse, so its value is g of 0. Next question. Consider the following statements m of t and m cap of t, where m of t is a message signal and m cap of t is a Hilbert transform of the message signal. So message signal is m of t and Hilbert transform is m cap of t. Next, from this image, modulation and in-phase component and quadrature phase components are given. If the signal is DSB-SC modulated, then in-phase component is message signal m of t and quadrature phase component is 0. If signal is SSB with upper sideband transmission, then in phase component is 1 by 2 m of t, quadrature phase component is 1 by 2 m cap of t, that is Hilbert transform. Next, SSB with LSB signal transmission, lower sideband transmission, message signal is in phase component is 1 by 2 m of t and quadrature phase component is 1 minus 1 by 2 m cap of t. Similarly for the vestigial sideband with vestige of lower sideband transmitted and vestige vestige of upper sideband transmission. For the question given, the correct option is 1. So for DSBSC, it is m of t into 0. For upper sideband SSB, 1 by 2 m of t is the in phase component and 1 by 2 m cap of t is the quadrature phase component. Next, for LSB into for LSB lower sideband, for upper sideband SSB is 2, it is 3. So from here we have to draw the line. Next, for C it is 5. So this is the answer. For C it is 5. So correct option is 1. So from this tabular column. Next question. product modulator, low pass filter, and local oscillator is given. So this is DSBSC demodulator. So S of t signal is given. Various DSBSC demodulators are coherent detection, Costas receiver, and squaring loop. Correct option is 1. Initially, the coherent detection of DSBSC wave. In the coherent detection of DSBSC wave, the baseband signal m of t. In the question, it is V naught of t. It can be recovered from the DSBSC wave. So here it is DSBSC wave, and this is message signal m of t. The baseband signal m of t, or as per the question, V naught of t can be recovered from the DSB-SC wave S of t by first applying S of t with a locally generated sine wave, and then low pass filtering the product. So product of this S of t signal and locally generated signal is V of t. So this V of t signal is passed through a low pass filter to obtain the message signal m of t. Coherent detection of DSB-SC wave. This diagram is coherent detection of DSB-SC wave. Next question. Consider the following statement in the context of analog modulation scheme and identify the correct option. So message signal applied to a integrator and then phase modulator will give frequency modulated signal. Message signal generated, statement Q is incorrect because message signal generated and given by the differentiator first and then phase modulator. It is not a differentiator, it is integrator. Integrator and phase modulator will give FM signal. Differentiator and phase modulator will give the PM signal, and zero crossing of FM signal. Angle modulated signal no longer have perfect regularity in their spacing of zero crossing. Zero crossing refers to the time instant at which waveform changes between positive and negative values. So some difference, zero crossing spacing of angle modulation no longer have perfect regularity as amplitude modulation does. And one more thing is, angle modulated signal has constant envelope. The envelope of amplitude modulated signal is depend upon the message signal. Zero crossing of FM or PM signal, that is angle modulated signal, does not have perfect regularity in its spacing. It is irregular. Angle modulated signal no longer have perfect regularity in their spacing of zero crossings. So statement P is correct and statement Q is incorrect. Next question. Compute the modulation index if V maximum is 10 and V minimum is 5. This is a amplitude modulated signal. V maximum is represented here and V minimum is represented here. The value of V maximum is AC into 1 plus mu, or V maximum is AC into 1 plus u, and V minimum is AC into 1 minus mu. In the question, V maximum is 10 and V minimum is 5. Then modulation index mu is V maximum minus V minimum by V maximum plus V minimum. So its value is 5 by 15, that is 1 by 3, 0.33. Modulation index is 0.33. Modulation index of AM signal is V maximum minus V minimum by V maximum plus V minimum. So V maximum and V minimum are the maximum and minimum values in amplitude modulated signal. Maximum and minimum values in amplitude modulated signal.